Hey everybody, I wanted to take this video here so you guys can see the original kick experiment live. And so the first thing I'll do is show you the test setup that I have. Over here in this corner we have the MOSFETs that not MOSFETs, but the SSR boards that I put together. I built this little base here with a bunch of these binding posts to make all the connections much easier. So these are all connected to the controller here, which is, as you can see, happily humming away over here. And over in this corner, I have two of the three channels actually pulsing the coil right now. I'm not using the third one for anything yet. And those two first channels are connected in parallel to the coil, which is right here. And the coil has a flyback diode across it. In this case, it's an MUR 410. And just to repeat the coil specs I mentioned on the post, this is 47 turns of 22 gauge copper wire around an empty Radio Shack spool, which is about an inch in diameter and about an inch and a quarter long, if I remember correctly. It has a resistance of about 1 ohm and a inductance of 24 microhenries. So if you guys want to reproduce this, this is a very quick and easy experiment to try. Right here I've got a high voltage scope probe here. This one is 4,000 volts, 100x impedance, 250 megahertz bandwidth, so we can still see the kicks without too much trouble. And of course that's plugged into channel 1 of my oscilloscope, which is also connected to an isolation transformer to protect it from any ground surges or anything that might try to blow it up. So now with that said, I'll go over here, and one more thing I forgot to mention. This circuit here, I've got a step charging capacitor circuit. This large black capacitor here has a rating of 3,500 microfarads at 450 volts DC, and I've been able to step charge it up to about 220 volts. So we're going to use this as our adjustable high voltage power supply so that we can see what happens to the kicks as we raise the voltage on them. And this multimeter here will be monitoring the DC voltage across the cap that we're pulsing the coil with. And to adjust that voltage I use my function generator, which is connected to this solid state relay over here, which is pulsing voltage into the microwave transformer to make the high voltage. So as for pulse settings, as you look here on the controller software, we're doing it at 15 kilohertz and we're using 100 nanosecond wide pulses. At the moment I have the delay set at 0, and what I'll do is I'll turn on each channel so that you can see what the pulses look like individually on the scope. And then we'll do a frequency sweep, or excuse me, delay sweep, between 0 and 500 nanoseconds. I found 500 nanoseconds seemed to be a decent spot, although for this particular coil the pulse height seems to be pretty wide-ranging. It's not as tight a tuning as the original test in Tennessee that was done. So first I'll go ahead and just turn on these two channels so that you can see what's going on here. So I'll go back over here to my computer, and we'll turn on channel 1. And channel 1 is now active. And if we look here on the scope, you can see this is the first pulse by itself. As far as our voltage, again, we're running at, looks like 43 volts, and it's falling a little bit because it's on, but I can readjust that to level it off a little bit. So, this is looking at the scope at 20 volts per division, and we also have our peak-to-peak voltage measurement that we'll be using later to see how the kick changes as we sweep it. So, this is channel 1. We'll go back to our controller software, and well, let's turn off channel 1 first. So, turn that off. And turn channel 2 on, and you can see channel 2's pulse. They look a little bit different. I'm not really completely sure why at this point. I've got the same MOSFETs in the solid state relays, so might just be differences in wire lengths, or the fact that this binding post is directly connected to the ground of the capacitor, whereas this binding post is connected through the small piece of wire to the same ground line. So we don't have a ground plane, so our pulses are going to have a little bit difference in them, but it doesn't seem to have a significant impact on the output here, so not a problem for our test. So now I'm going to go ahead and turn on both pulses so you can see what they look like together right on top of each other. So we'll go back to channel 1 and turn it on. So now with both channels on, we get a pulse that looks like this. And that's the basic idea here. I'll back it off so it won't be too fuzzy for you. And if I widen it up, you can see it's got a little bit of ringing and oscillations on it. This is probably the resonant frequency of the coil, or maybe the drain capacitance of the MOSFETs that we're seeing here. But for the most part, it's a pretty decent pulse. And again, this is measured directly across the coil, not between the solid-state relay switches and the ground, but across the coil itself. And in case I didn't mention this, this is a low side switch. So on the positive side, we have the voltage coming in, go through the coil, and then we go to our switches in parallel, which switch it to ground. So, now with that being said, I'm going to go ahead and start the delay sweep so you can see what happens as we change the parameters on here. So I've already got this set up and ready to go, so I'm just going to hit the OK button over here, or the start button actually. And here we go. So you can see it's starting to add a delay. And let's watch on the scope. You can immediately see that as it sweeps out, the pulse gets taller. And once we get to 500 nanoseconds, it'll stop. But you can quickly see that. I'm going to redo that sweep again since you kind of missed the first part of it. But that's what we get here with the kick on the second pulse. So it's twice as tall, and actually right here, according to the scope, we're seeing what looks like 83 volts. Let me double check that again. Yes, actually about 85 volts, so quite a big pulse there. But I'm going to go ahead and restart that sweep again. So if I go back up here, back to run sweep, and we're going to restart that again. Okay, and it didn't restart, so let's redo that again. Hold on just a moment. Oh, looks like the software froze up. But anyway, you can basically see this is what it looks like when it's running. So now what I'm going to do, since the software is basically stuck at the moment, is to go ahead and raise the voltage on this and see what happens now. So right now we're at 20 volts per division. I'm going to change it to 100 volts per division, if I can get it to trigger anyway. There we go. Okay. So we're looking at, excuse me, that's 50 volts per division. Our voltage on the cap is about 30 volts, so I'm going to go ahead and lower the input frequency, which is going to cause the cap to charge up now. And we're going to see what happens when we get over 100 volts on this thing. So here we go, cranking it up. And as you can see, voltage is rising, and so is the kick height. And we're rising, and we're still rising. And oh, wow, that's weird. There's a third kick showing up out of nowhere. Where did that come from? And there's more kicks. Ooh. Okay, I think I'm going to turn this off now. This is getting kind of weird. Wow, okay. Off, off, off. Whew. Okay, that was strange. Yeah, you guys are going to love this. Anyway, yeah, we just had more kicks appearing out of nowhere. This might actually be because of the MOSFETs re-triggering or something, but I don't know. I'm just guessing. Anyway, well, there you go. We'll see what you think about this.